All right, so as we mentioned yesterday, today we'll be doing one example and then we'll be doing the MATLAB code for it, okay? And I'm gonna add one more thing, but one thing at a time. Okay, so example. I want to do something very simple over here. Okay, so for the system below. So let me do a figure. So we're gonna have a spring. We're going to have a damper. Okay, we're gonna assume over here no friction. So K, C, and M. I'm gonna say our origin for the coordinate system is gonna be the center of the mass, so we call it X. And we'll be dealing with the initial conditions of X sub naught will be equal to 5.0 and X dot sub naught, so the velocity at 0, to be equal to 1.0. Okay, so just for practice, we're just gonna go through the whole system. So let's say step one. Determine equation of motion. So in order to do that, what do we need to do? We need to do some type of free-body diagram. Remember, we needed to do two. One for the left-hand side, one for the right-hand side of the equation. So the forces being applied is the force of the spring, damper, gravity, and normal. And the motion of this will just be MA or MX double dot. If I go too fast, let me know, okay? So determine the equation of motion, which will be step one is free-body diagram. So step two would be to use whatever. Motion is only translation, so we can do summation of forces equals to MA. Only on the X direction. So this will give us what? Negative KX minus CX dot will be equal to MX double dot. I mean, you have done that quite often so far. So the equation of motion is MX double dot plus CX dot plus KX equal to 0. Okay, so let's give some data to this problem I forgot to give you here. Let's say that the mass is 200 kilograms. The spring has a stiffness of 1,000 Newton meters. And that C is, let's say, 100 Newtons meters second. Okay, so that's when things start getting a bit more complicated because we have different forms to rewrite the solution. Okay, so let's just rewrite the solution above. So look at the notes. And let me know what was the expression that you had for the critical damping from the derivation. You need to look at the notes. Actually, it was defined, we said that the damping ratio would be equal to C over C critical, and that the C critical was the value for which the term inside the root was equal to 0. Okay, sub B. When you need to go back to the notes, I have the notes, but let's see if I have them here. I mean, that's where I cannot rederive everything every single time. So let's see, share if I have these ones. ME400. So let's see, summer lectures. So I'm guessing was lecture 4, probably.
I have CC equals 2m times omega n.
Correct. So it's that one. So we have this one. Blah blah blah. So it would be this term when it's this term is equal to 0. It's now basically. I don't know if we are divided here. So critical damping, this is when this term here is equal to 0. So that's what you should have on your notes. So CC should be equal to 2m omega sub n. Okay. We need to start knowing how to go to your class notes. So it's 2 omega sub n. Okay, and what is omega sub n? What will be omega sub n equal to? That one you should know. No. What is omega sub n by definition? Is the natural frequency. So it's k over m. So here, if we do the numerical application, we get C sub C equal to 2 times 200 times 1000 divided by 200 square root. And if you do this calculation, you get 894.4272. So why did we do all this stuff? So that we can go now to this equation. So that the critical damping XC, which is equal to C over C critical, will be equal to what? 100 divided by the 184.4272, which would be equal to what? 0.118. Okay, so it's just a matter of notation. You can select use to another one, but so in this case, what we have, XC is lower than 1. So what should be this case then? Under damp. All right. So now do you remember, I think I posted online a handout. Okay. So you don't have to rederive it every single time. So I think from the handout, so yeah, maybe I found one that was a little bit better than the one I gave you. But let's say from handout, correct me if this is one or not, the general solution For the, I mean, really it's for anyone, but let's say for the underdamp case is given by what? X of t equal to the exponential of minus xe omega sub nt time x sub naught cosine damp frequency t plus x dot sub naught. So I'm copying this directly from the note, so that should be on the handout. So this is including the initial conditions. All right, this gives you the initial conditions. Sine omega dtt. Okay, where in this equation, the damp frequency, we know it's equal to 1 minus x squared omega sub n. Okay, so this should be the basically the analytical solution. All right, so let's call it here. Again, I'm not rederiving the equation. I'm just giving it to you, okay? Let me look at something here very quick. I don't know if I saved it. I know I saw it, but I don't know if I saved it or not. What is this? Oh, this is probably what we're going to be doing now, I guess. This is what I gave you from where I got it, probably this is from where I got the response, no? For the underdamp, you see over here, this is probably the expression that I just copied, no? Okay. But I know I found one that was good. I don't know where I put it. Maybe here. No, okay, so I don't have it. I know I saw it online, but I don't have it. Okay, so what we're going to be doing now is basically just do a general solution that will work for any one of the cases, underdamp, overdamp, or critically damp, no? For a MATLAB code. So go ahead, since you have computers, open your MATLAB. So hopefully I can do it here. No, not long enough. Okay. Well, tell me, oh, I thought for a second they did not have MATLAB.
No.
Your keyboard is not working? You have plenty of computers to pick, so I don't think it's going to be an issue. So basically, I just started this. The first thing I do always is to clear everything, all the variables, clear the screen. And I mean, you can do as much typing as you want. I'll just do this one here. I might skip some. So the first thing will be, then it will be input data. So what do we have? N equal 200. If you want, you can put this is the mass in kilograms. What do we have then? K equal to 1000. You could say what? This is the stiffness in what were the units we use here? Newton. Oops. Newtons per meter second, no? Oh, no, this is Newton per meter, the damping. And then the damping, we had 100. And this is, yeah, viscous damping, Newton per meter second. And the second is divided, but I mean, again, it's not that important. Okay. The other thing we have as well is the initial conditions are given to us, which are what, like x naught equal to 5 and v naught, oops, v0 or v naught, yeah, equal to 1. Okay, so let's say over here, let's say here damping ratio. I mean, the letter is XC, but let me just call it CI, is that okay? Or XC. That we know this is by definition what? C divided by C critical, that way it's all C's. So we say that, let's see, omega sub n, we say what's equal to the square root of K divided by M. All right, the critical damping ratio we say is 2 times, oops, not 12, 2 times M times omega n, which is the natural frequency. Okay, so that XC, which I call here CI, we know will be equal to C divided by CC critical. Okay, so here I think there's multiple ways to do this in MATLAB. I think probably the most elegant would be to use the case, but I think I haven't used case for a while, so let's just use the if. So let's say, let me save this file, save as. Maybe let's save it for one of these semesters. So this PC, that's 400. Summer 2023 lectures. Okay, here it says so. Analytical. Okay. Analytical. Solution. SDOF. Okay, so here we're going to look at the different cases. So let's see. Different cases. I'm going to do with the if command. I haven't used the cases command for a while. So let's say if CI is equal to 1, this was the critically damped, no? So everyone can see over here, display critically damped. Okay, in that case, we need to go here again to, let's say we have to go to this one, critically damped. We can go and use this notation here, no? Okay, so you see this is XC1, C is equal to C1. We can do here this expression. So, I mean, we could just copy this one, no? Almost. So just copy this one. It's different than the code I have up front, but who cares? Okay, let's use this page over here. It will be minus, okay. So basically the response then will be x of t will be equal to exponential of minus omega n times t, which is the, why is it changing that stuff, times t. All right, so we need to copy that expression here, minus omega t x sub naught. Okay, so we have times x sub naught plus, look, there's a parenthesis here of v sub naught, which again will be v, oops, is v sub 0 not. Maybe I can do this one smaller on the side, so being open and closing all the time. Well, now it's going to be too small. Okay, that's too small. I cannot read it now. All right, so let's see, is x plus, okay, so we do this one, d omega is n or d order? Omega and t. All right, plus this or not, plus omega n times x sub naught all that stuff times t. Okay. Oh, what happened? Okay. Okay. Then we can do else if c higher than 1. We can say here display overdamped, that's it. In that case, we can write x equal to, let's see, overdamped overdamped. Is it there?
No.
Okay, so on the page, I guess, was current. This is the stuff on the note. So did I put it here over damped? Put in here anyway, so okay, over damped. You see, we could use any of these solution over damped. Which one do we have over here? All right, so okay, so if I read this, the x of t should equal to what? Let's say, let's call this one C1, and then we define C1. Okay, I will define C1 on top. Afterwards, equal and C2. I will define that later on. But it just write this one first. So x will be equal to C1 times exponential minus of C plus SQRT of C squared minus 1. And let's see, where do I need to put this one here now? Outside this one times omega n times t. All right. Plus, I can just do copy paste over here. Will be the same thing. I have to make this one a little bit bigger. This one a little bit smaller. This one a little bit bigger. So this one should be now C2. And the only thing changing is the sign over here. So C minus the square root over here. And I want to find, oops. Okay, now I need to write C1 and C2. So C1 is minus, let me put parentheses to be safe, x sub naught times omega n times C minus SQRT C square minus 1 plus the naught. Okay. Divided by 2 times omega n. So really it's omega d. Let me just call this one omega sub d. Yeah, that's omega sub d. Okay, and here we can write omega sub d will be equal to the SQRT.
Percent C1.
Omega d, isn't it omega d equal to omega sub n? All right, let's just forget about this. Okay, I don't want to. Let's just copy as it is over here. That way it will be just simple. All right, so critically damped, over damped. Let's forget about this one. Let's just write everything. I was trying to, so 2 times omega sub n. Because this term over here, omega sub n, this is the damp frequency. Times SQRT of C square minus 1. Hopefully it's not typing errors here. Control copy, I do copy paste. I think the other one is similar, not equal, but kind of similar. Let's see what is changing for C2. C2 is just the front is positive. So this one is positive. And this term over here is positive in the bracket. So this one here is positive. All right. And everything else is the same. Okay. Else, if C lower than 1, we can write display under that. What did I write? Under damp solution. And if you want, since we're using this class notes here, oh, here you see we have the overdamp on this one. Okay, I have them over here with the solution and everything. All right, so the way to, okay, under damp, they use this one here, since we have it. They use this one here, so we have x will be equal to the exponential of minus C times omega sub n times t. I don't know how to do this stuff, that doesn't write, okay. So this is the exponential decay times x sub naught cosine, oops, times cosine omega sub d times t. So we need to define this one here anyway. Plus d naught plus C times omega sub n times x sub naught divided by omega t. Okay, now I'm losing tracks of the parentheses. So let's see. This one is going to close with this one. So here I forgot to close one. We got t. Okay. All right, so this one is going to close this one. Okay, now here times sine of omega d times t. I think that should be it. So you see, we need to define what is the omega damp. So maybe we can divide it here or whatever. Maybe here, it doesn't matter. Omega damp is equal to SQRT of 1 minus C squared times omega sub n. Okay, so hopefully that will run. And so I'm going to run it, see if there's any error for now. What? I don't know. Did I forget something? Oh, we need to define t, no? Okay, correct. So for t, we can define t. So let's see. So t might be changing. So let's say, let's come over here. Define it some over here. So time. I'm going to define it a bit differently. Let's say I'm going to call dt here. Let's say 0.05. That would be the time integration. Let's say and the number of steps. And this is the reason why I'm doing this. You will see later. It's not needed for this. So T max will be basically dt times n. That will be the total amount of time. So that t would be equal to simply a vector that will go from 0 to dt to T max. So hopefully that will work. All right, so let's see if we run it. So line 38, what is it saying?
Well, negative into the exponent.
Oh, in here?
Yeah.
I need to open parentheses here then? Is that what it's saying?
So,
Oh, I can put,
like EXP,
yeah, I don't need, you're right, I can just put it here.
and then you need that for
For the other one as well? For 30?
so 35, line 35, it needs to be EXP,
Oh,
and
okay.
in parentheses, negative 1 times CI.
Okay, so I need to open the parentheses here. What was before the arrow that it gave me the arrow? Here we have the same thing. So why is not giving me the arrow over here? Oh, because it's skipping this one.
Right.
So this one, we can just do it this way. Okay. Let's go one by one. Here, this one looks correct. This one looks correct. So this one, did I just change something here? Did I remove the minus? Yes, no? So in here, how can I do this? So I need to open another parenthesis.
Are you asking for like the, so the negative before the parentheses doesn't allow the exponent to, or not the exponent, doesn't allow like me to have input arguments. So you need to put the negative inside of the parentheses.
Yeah, but then I would just be doing this term over here, not the whole thing.
So then you can do exp.
Open a parenthesis.
And then to the power.
That's what I'm saying. So my only option is to open another parenthesis.
Yes.
Okay, we'll do this. And here what's working. I think that's it, no? Okay, and I guess this one, I know what this is going to be. Line 38. So what happened here is that for the t, since this is a vector, it wants to do the scalar multiplication. So you're going to have to put a dot in front of every single t. That's my guess. Did I miss one? Dot, dot. This one is done. I guess this one I did not do it yet. Done. I'm done. Let's see now. All right, so line 38. So let me see which one is not doing. I mean, you can put it in front of everyone, but I want to see which one is not doing. So let's see if I need to put it between these two. I'm gonna have to put also one between these two. Okay. I'll put it here. Okay, was that one work? Okay. Okay, what did I do wrong here? I forgot in a parenthesis or what? Oh yeah, I forgot that one. Okay, so I think it's probably that. Okay, so now it's running, okay? You need to put a point here as well. Between these two. This is because it wants to do the scalar product. Okay, so let's see. So let's do plot, figure 1. Yeah, would be equal to what? Okay. Plot, so t versus x. X label with the time in seconds. Y label with the response x of t in meters. Okay, I don't know if you want this or not, but generally I like to put read on. You can put a title. Let's see what it does. Okay, so this is basically going to show you the response over here, no? Okay, let me try to do something as well, which again, I have a different notation, but since we have time, okay? So this is like if I was doing myself in the office, okay? Hopefully this will work. So what I will do, I will also like to plot the, remember like the circle to see how it's going. So in order to do that, we need the velocity, no? Okay, so we know x, but we don't know the velocity. So how can we find the velocity? We know the formation. Velocity is equal to dx dt. So we need to take the derivative. Okay, so MATLAB can probably do the derivative. I'm sure MATLAB can do it, no? And maybe I can put here. Let's try it. Maybe I don't even need to do anything. Generally, I like to do it on a different program, but v will be equal to, how can it be done in MATLAB? Differentiate x with t. Would that work? Okay, it's gonna work. So let's say now if I say figure 2, if that works, that will be very easy. Figure 2, I'm gonna plug X versus B. Let's say a few runs first. Okay. I'll represent function variable V. Oh, on the wrong one. Okay, yeah, on the down. Yeah. So maybe that's what it's doing is oh, okay. So that doesn't exist. I thought you could differentiate in MATLAB. Okay, doesn't want to do it. No, basically. Personally, what I would do is, if you ask me what I would do, hopefully it's Maple. I will go to Maple. But why is not doing it? That's very strange. He did it before, no? He didn't give any error for this one. Let's try again. D equal differentiate X, C, and let's just keep it over here. Okay, so now let's remove that one, but let's say, and this is what I want to do, no? Let's give the error. Oh. No, I know what it is. No, I know what it is. What happened is that T is taken as a number.
Yeah.
So, yeah, so, I mean, what I would do is this, if you ask me, I will come here to this. Well, I haven't used this in a long time, so I don't know which one to use. This one? What did I do here? I'm gonna exit this one and just say, okay, what's the new document? Start working. Okay, so how did I do this stuff? I don't remember much about this one. I would do a restart. So it clears everything. Then I will come to MATLAB. What is the expression we want to do over here is the on the damp. I will take this expression here, copy paste, Control B. You need to put here 2 points. Enter. What's happening now? Ah, okay. I don't think it's recognizing these points over here, these dots. I think that's what it is. Hopefully, that would be the only problem. Okay, and now what I would do, I would just say V equal to differentiate X with respect to T. And here we go. No? Yeah? I mean, maybe I could say, I don't know if it's going to do anything. If you want, you could probably do this. I don't know how much it's going to simplify, but I would like to take, it doesn't matter because it's just a matter of copy paste. Okay, so I don't know if it's Peter or Ogre, no? Let me remove the simplify. All this happening too much. And that way, term by term. So start this and this. Okay, now I will come over here. I will copy paste this expression here. And I will put it here under the V on the damp. This is going to go crazy, but that way you show exactly the way I will do it in my office. So here we go. We need to see omega, blah, blah, blah. Then I think hopefully this is not going to go bad. I mean, you could keep everything in one line. Let's keep it first, everything in one line and see what happens. And then we can make it a bit clearer or not. What error is it giving now? Oh, we need to report now the dots in front of these ones. Omega t. Always not recognize it. Dot t. 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 And I'm sure we're gonna have to put all the dots. Let me try to put in some other places. This one might be needed as well. And this one, let's see what happens. Okay, and now you will see, in addition to the other one, you will have the motion this way, no? Okay, so this will be, so X ever will be response X of t, and the Y would be velocity Vt. Let's remove the units, and this will go like this. So the first one will give us the response in function of time, no? But basically this figure here and this figure here are exactly the same. No, they represent the same. So maybe you can do it on your own, or you want me to do it. So what do we do next? We did it for this one. Let's see if we can make it look pretty, this one. Sometimes that creates problems with me, at least in MATLAB. Supposedly you're able to do this, no? But it always creates problem with me. So let's see. Is it running? Okay. So as long as it's running, you can create those points. I will put some other, so that if you print it, everything fits in one page, but it's just the command line. But I will do one by one because sometimes it creates issues. Don't ask me why. I have no idea. Okay. Okay, so let's say if we wanted to do now for the, let's do further critically down. We could do exactly the same thing, no? Yeah, I could come over here, copy, paste, I go to Maple. Let me delete all this stuff. Control V, X this, and you need to remove the points. Here we go. Enter. V equal to differentiate X with respect to T. Here we go. Copy, paste. What did you do here? Omega and T. Well, did okay. I don't know. Hopefully it's going to go right when I copy paste. Control copy. So this was this one. We need to come here. Control V. So V would be equal to omega times n. You have to put here the dot. Here as well. Here as well. Here as well. Here as well. Maybe. I don't know. So maybe we need to do this. 1, 2, 3. Okay, so here I'm a little bit surprised. I don't know if it's, I mean, I don't know if MATLAB needs to this to, does it go inside here to compile it or not? If there's an error here, will it find it?
Yes.
Okay.
If you have, as long as the ellipses are there, that's good.
Okay. So we did the critically damped, the other damped. Now we need to do this one. This one's going to be a lot more. Right. We could do this one as well, no? So we are doing it. So Maple. I mean, you see the way I will do it? C1 are constant, so it should not change anything. So this, oops. Oh, you need to remove the dots. There's only one dot here. Oh, so easy then. Okay, so I need to create another execution file. This one, v will be equal to differentiate x comma t. That one doesn't look that pretty, but doesn't matter. We just do copy paste, no? Okay, now it looks a lot better. Did you take the derivative? Oh, let's see. Let me do this. Okay, is that it? So yeah, this is one here. Okay, okay, that's it. Let's trust MATLAB. Midpoint. Overdump. Oh, and here, even if you want, you see, you could move this one to the next line, but it doesn't matter. You don't have to put. But what happened to the T here? We lost it. Something wrong happened here. Something not right here. We lost the T here. Yeah, let's see what's happening here. So what happened to the T? Resume recording. So please pay attention to this when I was recording. Okay, so now it looks like that we should have everything, no? All right, so all right, so now you see to do the analytical solution, I mean, once you have it, it's okay, but can be a bit long in typing, no? Okay, and you first need to find the equation and everything. So the equation of motion, we need to find it every single time. Okay, but there's another way to solve this, and it is to find the numerical solution. So let's say the equation of motion is generally solved numerically using the explicit numerical approach called Bloom-Hekuta method. Okay, so over here, basically this is pretty simple. Again, I'll do it for you, okay? But basically, remember that we have the equation of motion is mx double dot plus cx dot plus kx equal to 0. This is our equation of motion. Okay, so what we do is what is called, you rewrite the equation of motion, which is on x double dot, okay? What happens is that you want to be able to rewrite this equation just in function of x dots and x. Okay, so in order to do that, you need to do what is called the space state representation. So what you need to do is assume a new variable. So let's say assume y equal to x dot. Okay, let's say, all right. So now let's say you can rewrite a new variable z, where you will have z will be defined as x dot, where here this is what the initial displacement. So this should be our x sub naught, and this one here will be our initial velocity, x dot sub naught or x sub naught. Okay, so this is all the same. I just rewrite this a little bit differently, but the important thing is that we have x dot. Okay, this could be just to the notation, could be the same as x, y, but it doesn't matter, it's just notation. But what's important is that now, if you do z dot, this is going to be equal to what? X dot, correct? Or if you want y dot, which this should be the same as x dot, x double dot. It's all notation, okay? So this is not that important, or this could be equal to what? Y, because by definition, y is equal y dot. Okay, and this could just be y dot. Okay, so now recalling the equation of motion, we have mx double dot plus cx dot plus kx equals 0. I can take this equation, I can divide everything by m, so it will be x double dot plus c over m x dot plus k over m x equals 0. Or I can rewrite this one as x double dot will be equal to minus c over m x dot minus k over m x. Okay, then let's go back to this function over here. So we're gonna have z dot will be equal to what? I mean, it's different ones, but z dot could be equal to what? To x dot, if I use this formula here, will be x dot, correct? Divided by x double dot, no? But what would be x double dot? This expression here, the one we need to replace. Okay, so it will be now minus c over m x dot minus k over m x. Okay, and I call again, I'm not expecting you to understand. I give it to you this. Once you know how to do it, it's very simple. Okay. Now, x dot over here, if you lose at this vector here, what would that be? Is the second one, no? Yeah, so it will be z2. Now, this one will be equal to what? Minus c over m. This will be x dot. So this should be again z2 minus k over mx. X will be z1. Okay, so this is what is needed for MATLAB. So this is the input for the MATLAB solution. Okay, and that's what we're going to be doing now, very quick. Okay, so we go here, go to MATLAB, create a new file, new script. Okay, and that one just gonna call it, actually this would be a new function, but let's say function. Have you used functions in MATLAB before?
Yes.
Okay. So function f would be equal to the function 1 in function of t and z. Okay, so I might be missing something here, but okay, doesn't matter. So we're gonna have, the way I define this, I don't know if we'll be able to use the math over here or not. F, doesn't matter, you can call this whatever you want. Zeros of this size will be 2 and 1. Okay, so I'm gonna call F1 will be Z1. This is basically our X, but I want to mix the X. This would be X dot, and F2 will be the X double dot that we say was equal to what? Minus C over M times Z2 minus K over M times Z1. Do I need to put the variables that I'm going to be using here, like M, C, M, and K? Yeah, I can do this.
You can define it in a function, but otherwise, if it's in degree on animal, you think I have to.
Do you think I'm going to have to put them here as well?
I think so.
Okay. Let's put it here as well. I think you can define in some old MATLAB, I think you could define some variables as global. But let's just do it here. So what was M in this case, 200? I want to finish this. So M equal 1000 and C equal 100. Okay. You might not have to put it here. I don't think so, but. And then, I mean, sometimes it's useful to put return over here, but sometimes you don't have to. Or M. So what we're going to get here is T and Z from this expression. So file, save as, the function 1, let's solve it with this one here, save. So hopefully this will work. all we have to do here is come over here and say, whatever. Hopefully this will work. Analytical solution. So I think a solution, we know our initial conditions, so let's say Z0 will be a vector that we said before with our initial conditions was equal to X0, comma, B0. I don't know if I defined it before or not, but it should be our initial condition. And now all we have to do is say our output T and Z. We should use the same T as before, will be equal to ODE45, which is for longitude of 45. This is going to define the D function 1. Okay, we defined before the, we defined T max and so on, but not the rest. So let's see. So T span will be what we called before T. Yeah, so T. Hopefully it's not going to consume the stuff. T. And we need now the Z naught. Hopefully it's not going to get confused with the, okay, and here if everything goes fine, let's say figure 4, plot T, comma, Z, everything on the solution 1. Okay, so let's pray that we don't get any error. Okay, it plotted something but doesn't look correct. Okay, so what can it be here? Only thing the function can be error here is here. Okay, so I think the only error can be here. So let's see. M200, 1000, 0, F1, 0 to 1. F1, here we go, should be Z2. Yeah, F1 should be C2 and see how that works. You see, this is the response. This is the same as figure 1, no? Almost. This is the analytical, this is the numerical solution. So this is the analytical solution, this is the numerical solution. Okay, so let me finish this very quick. Maybe let me add some stuff over here. This is title over here that you can use in MATLAB, or we'll find out. Me neither. Numerical solution, but if it's not saying anything, no, should be good. Control copy numerical solution, figure 2, numerical solution, figure 4. We're gonna say this is, oops, sorry. Reverse, this should be what? Analytical solution. Sorry for that. Analytical solution. Figure 2 is analytical solution. This should be numerical solution. I can copy this, all this stuff here. I can take figure 5. Figure 5 would be this time Z1 over Z2. Oops. And it should be All right, so here we go. Okay, so basically, why didn't put numerical or anything like that? Okay, so I forgot the numerical. So, I mean, here you see the two analytical. I should put here the numerical solution. And basically, you see what happened. Now, the numerical solution for this one is basically come on. I mean, you see what I mean. Now that these two figures here look kind of the same, no? This one, the analytical solution with the numerical solution, they kind of give the same response, no? Okay. And the same thing if we look at the other ones, obviously, if they do the same response, this is the analytical over here, and this should be the numerical. They kind of give exactly the same response. Okay, it can be some small differences, but in this case, you see where it is, no? Okay, so as you can see, sometimes it can be long to do the numerical, the analytical solution, while on the numerical solution, the only thing you're gonna have to change in this code if you want to do it is basically this function over here, no? Yeah, and everything else should be the same. So we have 4 minutes. Any question? I mean, did everything kind of make sense or no? Okay, so were you able to do the codes as in class?
Yes.
What do you mean the exact opposite?
Like everything's just flipped. Like, the numerical solution goes like this, but then, or the analytical goes like this, but then the numerical goes. I can show you.
I don't know. I mean, but basically, I mean, I'm going to scroll this here slowly, the code. You will have it available online. You will have the video, okay?
Oh,
You want to go through it again. Yeah, I'm not going to hide this. I'm not going to give you the file, but if you want to look at the video, you can go and check. Okay.